Hello everyone and welcome to the course Design Board Fields with Confidence. This is the last video of the third part where we'll be talking about the questions we posed throughout this part and the answers to them. Now in the first chapter of the third part we talked about the difference between monthly and hourly temperature profiles, and more specifically about the importance of the peak duration when we are using just monthly instead of hourly data. And this question is all about how you can convert your hourly simulation towards a monthly simulation just by playing with the peak durations. Now, before showing you this answer in GHE2, I also want to already talk or introduce the second question, because there we were talking about the variable fluid properties and that we do not work with a constant viscosity and Reynolds number throughout the whole simulation period anymore in GHE2, but you can actually update the viscosity at every hour of the simulation, and this also had a quite tremendous effect on your results. Now, one side effect or one added bonus of using variable fluid properties is that you can sometimes suddenly see a jump in fluid temperature you would not expect, simply because your fluid temperature is now too cold and you go from a transient to a laminar flow rate. And the question was, how can you create or can you find a set of parameters so that you actually see this effect in GHE2, because it's quite rare. Now let us jump into the software, discuss these first two questions and their answers, and then come back and finish with this presentation and the other questions. So here we are in GHE2. I opened again our document we created in the first chapter of this part, and I duplicated it so that we can keep track of what we are doing. So it was a project where we simulated two buildings, residential and auditorium one, with both monthly and hourly temperature profiles. And if you can see here again, or recall, in our monthly simulation for the residential project, you are at 2.63 Celsius as a minimum fluid temperature and 16.95 degrees as a maximum one. With our hourly simulation, however, our maximum fluid temperature was lower, as well as our minimum fluid temperature. It was also lower, which you can see clearly here. It was a 2.909 degrees. Now the question is, can we come up with peak durations for a monthly simulation so that we match the values here in our hourly one? And to do that, I'm just going to duplicate this, let's call this answer, shall we? If we go to our thermal demand, we see that our peak duration is both 8 hours, it's the default value. But I know, as a matter of fact, that the peak duration in cooling of 4 and in heating of 115 will give us the best results. Now, how did I find out? Well, just by trial and error, basically. So if we set the peak duration for heating to 115 hours, we exactly match our 2.09 degrees Celsius we also had in our hourly simulation, as you can see here. Now a maximum limit here of 16.4, we cannot match that exactly, but if we use 4 hours for a cooling peak, we are close at 16.48. Now if we want to do the same for our hourly simulation, here we should match the values 9.8 and 16.19. But we are at 9.7 and 16.88. So both peak durations here need also to be smaller. So what we need to do is we need to get our maximum temperature at 16.88. It should be lower. So to do that, we should have a lower peak duration. Our minimum average fluid temperature is 9.71. It should be higher, 9.8. So here we also have to have a lower or smaller peak duration. And if I recall correctly, with trial and error, we need 3 hours in peak cooling and 5 hours as a duration for heating. And using these values, we should end up with a temperature limit that's quite close, so 16.26, which actually quite close to 16.19, and 9.80, which is quite close to 9.76. Now, the goal of this exercise was not to give you these definitive numbers that you can use for all your simulations. It's just to show that for the residential profile, in order to match it, we needed 115 hours in heating and 4 in cooling, which is a completely different number. In the case of an auditorium, we needed 5 hours in heating and 3 in cooling. So there is no a priori knowledge of what this peak duration should be. We can only match that if we know the hourly profile, we simulate it, and then reverse engineer what the peak duration should be. And this is just to stress the importance of using hourly data when it's available, because it gives you way more insight in how your system or your geothermal system behaves. Now that was for question 1.1. In the second chapter of this part, we talked about variable fluid properties. Now, to illustrate that, let us go ahead and duplicate our residential profile. Again, let's call this ANSYS 2.1. Little bit chaotic, all in the same project, but stay with me. And here we're going to say, let's work now with variable fluid properties. So what it now will do is, instead of working with constant properties throughout the simulation, we will update them at every month. And we here have now 2 different Reynolds numbers, etc. And you see our profile here. Now, if we want to see this sudden jump, what needs to happen is somewhere between this first and this 25th year, we need to transition from a turbulent flow to a laminar flow rate. Now, here you can see we're at laminar in extraction in the last year. 716, it's extremely laminar. And even during cooling, we also be laminar, and we're at 1363. So what we are going to do is we go to a borehole resistance step, and we need to make sure that we end in extraction with a laminar flow rate, but ever so slightly laminar. So not quite extremely laminar, but just 2100 or something like that. Because if it's almost towards the edge of transient regime, yeah, then we know that in the earlier years, when the fluid temperatures were higher, yeah, we will be in this transient regime and we will see a jump in the profile. So let us go ahead and just create a single U probe. Right? This already increases the flow rate, because now we have 1 probe instead of 2. And let's use 22%, 21% perhaps, 21.5%. Let's use 20.5% of monopropylene glycol. We are just, so you can see here in extraction, and let's use 22. It's a little bit more realistic. We're at 2100 Reynolds number, the last year of the simulation period. So probably in the first years, we will be higher and the borehole resistance will be better. So if we now simulate this, we would expect a sudden jump in the profile. And here you see our profile, and now at the first sight, you might not see anything. But for the trained eye, and I hope you already have a little bit of a trained eye here, you can see a jump. Now, this temperature drop, this sudden jump, it's basically due, well, it's the difference between the borehole wall temperature and the fluid temperature. And this is determined by, if you recall, the second part of this course, the borehole resistance multiplied by the peak power. Now our peak power is quite small in this case. So it's only 62 kilowatts. So even if our borehole resistance changes significantly, yeah, we don't see that big of a jump in temperature. Now what you can see here, and it's quite subtle, is that here, for example, in March, where we have a certain difference between the borehole wall temperature and the fluid temperature, 8.5 to 6.51, which which is a difference of 2 degrees. But if we go to, for example, the tent here, we can see it's 6.9 and we go to 4.55. So it's actually half a degree bigger. So yes, there is here a sudden jump, and you would expect the same 2 degrees limit difference, but here the jump is quite small, but you can see it is there. So don't be fooled when you don't see a sudden jump, it can still be there. So now let's go back to the slides and talk about the other questions we posed in this part. So in chapter 3 of this part, we talked about not the variable fluid properties, but variable flow rates. And we talked about this graph showing the first year of a simulation period, the borehole resistance here. And we questioned ourselves, well, if we thought back about the variable fluid properties as showing us that we can transition from laminar to turbulent between heating and cooling, we now see here that our borehole resistance is almost constant throughout the whole simulation period. Now, the reason for that is simply because our flow rate, constant flow rate, is high enough so that no matter our viscosity in heating and cooling, we always will be turbulent, at least transient. So you can see some ripples, you can see some noise, let's say, it's not a straight line, and that's due to the changes in viscosity. But here, the flow rate is high enough so that we will always be turbulent, so you don't see this sudden jump between the seasons when switching from laminar to turbulent flow. This you see in this case when you have a variable flow rate, because now the flow rate is variable, you will see this sudden jump between laminar and turbulent flow. Now a second question related to this graph is why there is a seemingly maximum limit around 0.35 meter Kelvin per watt. Now the reason for that is quite straightforward actually. And we discussed in this chapter about variable flow rates, about the minimum flow percentage. And we talked about that our pump, it cannot modulate between 0% and 100%. It will go down to 30, perhaps even 10%, but not lower than that. So this maximum limit at 0.35 is actually when our flow rate is topped by this 10% of the maximum rated flow rate. So if you set it to 20% or to 5%, you will see that this limits, or the seeming limit will actually be somewhere else. And that has, as we discussed in the deepening insights in the textbook, something to do with the numerical stability of the way the variable flow rate is taken into account. Now, the last chapter talked about not variable fluid properties, not variable flow rate, but variable efficiency. And the first question was about our standard SCOP given at B0W35, where 0 degrees is the reference temperature, the inlet temperature of your heat pump. Now, the question is, if we use this B0W35 value, what would be the average fluid temperature you use as, you use in GHG to the temperature graphs are always average temperatures between inlet and outlet. So if the 0 degree is the reference inlet temperature of your heat pump, what is the average fluid temperature in GHG2? Now to calculate that, what we need is the temperature difference between the inlet and the outlet, the delta T. Now if you use a constant flow rate, it varies of course, but if you use a constant temperature difference, it's a fixed value. Now typically it's between 3 to 5 degrees Celsius, so let's say it's 4. And this means that the fluid temperature coming out of our heat pump and going into our bore field is actually 2 degrees colder or 4 degrees colder than what goes in. So if we have 0 degrees coming into our heat pump, we know it's -4 coming out of it. So it's -4 in the bore field and 0 out of it. So this means that when we say it's a B0W35 value, we are working with regime -4 to 0 in the bore field. So this means that our average fluid temperature is -2 in this case. Now, question 4.2 was about the study with it. with residential, the office building, and the multi-utility building. And we said that, well, when we switch from 0 to 3 degrees as a minimum limit, we actually see that we need more borehole meters, except for the office building. And perhaps you noticed that for the residential building, if we go from 0 degrees limits minimum to 3 degrees, yeah, we need more borehole meters, we need a larger bore field. But why does it stay the same for the office building? And this has to do with the bore field quadrants, and perhaps you recall that, where we said, well, if our bore field is actually limited by the maximum average fluid temperature, which is often the case in an office building, quite a lot of cooling, so we're limited by our maximum temperature in this case. So changing our minimum from 0 to 3 degrees, it does not matter. It's no limiting factor. And that's why switching from 0 to 3 degrees here does not make any difference on our design or the required borehole depth, because it is determined by our maximum average fluid temperature. So this also stresses the importance of the bore field quadrants for this type of questions. Now, to end this video, we are going to talk about question 3 of the last chapter. And there we made a simulation in GHE2 with variable flow rates, and we made some sensitivity analysis. And what we did is we used the constant flow rates. Now, the question is, if we change it to a variable flow rate, and with a temperature difference of 3 degrees between extraction and injection, will that change our design? And how will it change our design? So let's jump again into GHE2 and answer this question and wrap up this whole answer video. So here again in GHE2, I opened up the course documents of chapter 4 of the third part. Now, if you're wondering where you can get this, it's linked in the textbook. For every chapter at the end, there is a file, the report of GHE2, so you can recreate these scenarios yourself. So in our fourth scenario, what we had is we simulated it and we had an average SCOP of 5.14. Now let us go ahead and duplicate this and let's call it scenario 5, deeper boreholes and modulating flow. So over in our borehole resistance step, we're going to say we're not going to use a constant flow, but we're going to work with a constant temperature difference, and it was 3 degrees and 3 degrees. Now let us go ahead and calculate this. Now what this would do is it will at every hour simulate the flow rate, the fluid temperature, and so forth. Hence it can take a little bit longer. But what we would expect is that our efficiency is slightly lower. We were at 5.14, now we are at 5.04. And the reason for that is that now that our flow rate is modulating, we are more in a laminar flow range. And in this laminar flow range, our borehole resistance is lower. And this means our fluid temperatures are lower, leading us to a lower overall efficiency. Now, what is also interesting is that our fluid temperatures are not identical. So if we focus first on the maximum fluid temperature, it's here in the case of a modulating flow, 18.75, and it was before 18.12. So it became worse. And the reason for that is that here we had a very turbulent flow rate in injection and a very good borehole resistance of 0.098. Here, our flow rate is still transient, it's not fully turbulent, and our borehole resistance is actually a little bit worse. And this means that our fluid temperatures, since our borehole resistance is higher, are also further away from our borehole wall temperature, and hence the higher maximum flow. Now, the same reasoning does not apply for our minimum fluid temperature, because here we are at minus 0.10 with a borehole resistance very close to 0.1, and here we have a borehole resistance also very close to 0.1 and a significantly higher minimum temperature. Now, to understand that, what we will do is we will zoom in to this minimum temperature, which is actually here. So it's the 7th of March. We see here that we have a minimum fluid temperature somewhere around here. And it's 0.26, it's actually 0.2 here. So at 6 a.m. in the morning, it's 0.2. Now remember this curve, because if we go to variable flow rates and we zoom in on this same point, so here the 7th of March, what you will see is that at 6 a.m. so slightly higher, it does not matter, but we have here this sudden jump that was not there before. There it was, we go down and we go back back up. But here we see at 8 a.m. a sudden jump. And that's because at this 8th hour in the morning, on the 7th of March, in our simulation, our peak power is slightly lower. It's not at a maximum flow rate. So we're no longer transient there. So we fall back into a laminar flow rate. This laminar flow rate has a worse borehole effective thermal resistance. And this also means that in this case, our fluid temperature there is lower. So this is an example of what we talked about earlier this video and earlier this course, that it can be that during a laminar flow regime or during an off-peak moment that your design is actually, that actually determines your design. So it's not always at the maximum power that your design is critical. Here it is at not the maximum power, but due to a lower flow rate there, that we have here at the 8th hour in the morning, actually our minimum fluid temperature. So this is what I wanted to tell you about the answers throughout all the questions in part 3 of this course. And I'm looking forward to seeing you in part 4, talking about the hydraulic aspects of bore field design.